And now I'm going to present to you those things that you need to know to conduct formal statistical tests. So far, we've been graphing and thinking about distributions and effects and so forth, but we have not yet conducted a formal statistical test, and today is an introduction to that. One quick point, which is we're going to go light speed here. Generally speaking, this class is a class about the analysis of biological data. It's not a statistics class. We are going to run statistical tests. The issue is that if you were taking a statistics class, you would need to be taught probability theory and do a lot of math, maybe by hand some of it. And we're going to jump in hyperdrive past all of that. And we're just going to arrive at a place where we're going to climb the mountain of statistics. And we're just taking with us the basic tools. That's it. If you're going to climb a mountain, you need some ropes and some carabiners and some kind of thing, and then a sleeping bag. What are the most basic tools you need to climb the mountain of statistics? That's what I'm going to try to provide to you here. It means skipping over a whole lot of stuff, irresponsibly, potentially. However, and I think like a math professor would say, this is malpractice, what I'm doing in the class, because I'm skipping all this stuff. The objective of the class, however, is for you to be empowered, for you to be able to do things. And so we have to skip a bunch of stuff. It's just it. And just get to the point. So we're not going to do probability theory, flip a coin 12 times or whatever. We're not going to do any of that stuff, and we're not going to do any of the statistics by hand either, which you would normally do in a statistics class. Do a t-test by hand and whatever. So then you like really understand the math underneath it all. But I'm just going to show it to you, just a quick peek, and then get as fast as possible to practical application. So we're just hyperdrive and just like, what are the basic tools you need? Practicality and application. Just a reminder of these 7 principles. We won't go through these all again, but yeah, all of this stuff underlies the tests. And it's really important, overarching philosophy of the class, that these basic philosophical, or the Tao, the way of doing statistics I'm trying to teach you, including things like this stuff about variation and sample size and all of this sort of underlies any statistical test. And regardless of what happens in the future, if there's some new statistics come around, or whether you're talking about cars or sports data or home data or biological data, whatever, all these things apply. It has nothing to do with R. Forget R. If R doesn't exist in the future, it doesn't matter. These principles still apply. So I just want to say that, and that if you get all this core stuff correct, then the statistical tests kind of are the least of your concerns. Similarly, or just like an extension, is this concept: let your analysis be guided by doves. I just made this up, and I think if you can get this through your head permanently, you'll be so much better consumer of data and a better scientist. And we're going to let all of our analyses be guided by doves. So the first thing in the doves list of attributes is distribution. We talked about distribution some. I'm going to definitely come back to this multiple times, because I think the underlying frequency distribution in a data set is a fundamental concept that you need to get. Obviously, it's D in doves. Here are some examples of frequency distribution: uniform distribution, bell-shaped distribution, asymmetrical with a left skew here a little. Here's a bimodal distribution. And we've talked already a little bit about this is a human weight distribution, and this is income distribution, where you've got a right skew, and potentially an extreme right skew. And I do have an example that I'll show you later in class. of real data that are outliers that would create not only a skew, but a skew that's somewhat unbounded. Here's a key piece, and I will try to hammer this a little bit. When you're thinking about distributions and you're thinking about this principle of understanding the biology of your system that you're working in, are there reasonable bounds that you're working within? In other words, for example, weight, and I will show an example of this. If we're like, oh, the weight of human beings in Ohio or something, and this thing's a little bit off, but this is like, oh, the median weight is 180 pounds or something like that, whatever it is. You could get somebody a lot heavier than that. And I'll use an example of Andre the Giant, who was a actor, played Fezzik. And that guy weighed 520 pounds. That's a lot. But it's nothing, it's still within a reason. I mean, it'll be off this chart a little bit, but it's still within somewhat reasonable, a reasonable or bounded distribution. Whereas with income, for example, you can have values that are mean annual income of people that are in the billions. That's extreme, potentially unbounded. Maybe there's not a right end to this. We know with weight, you don't have a 1,000-pound person. You don't know if there's a yearly income. Is there a bound out here? How much does Elon Musk make a year? I mean, at some point, it's almost infinitely. It's not infinite, but the boundary is way, 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 way outside, far, far, far outside the mean. So, 50, 100, or 1,000 times the mean. So this is just something to talk about. I'll keep coming back to this. But this is fundamentally, this idea of the distribution fundamentally underlies any statistical test. Here's a fundamental question. What do you expect to be the underlying distribution of your data? If it's, for example, I've mentioned nail depth before, just like how deep is, or like the length of your index finger. We can measure the length of index fingers and make a bell-shaped distribution on campus, easy. And there's not any index fingers on campus that are 2 miles long, right? So there's a boundary there. Maybe there's one 7 inches or something, but 2 miles is not a thing. So this is just like the underlying distribution of your data. Is it a predictable range or is it quasi-unbounded? There's a bit of quibbling about whether this fellow, whose name is Johann Carl Friedrich Gauss, is indeed the person who came up with the idea of a normal distribution. We call this a Gaussian distribution. I looked into it a little bit. It's not clear that this guy came up with it. We still call it Gaussian. And this is the standard bell-shaped normal distribution. And there's a lot of math under this. Just like, oh, within one standard deviation, this much of the data is under that curve, calculus style. Anyway, I just want to show you his face and say that we're going to be looking for this, a normal distribution. Does your data in your test approximate a normal frequency distribution, a bell curve? A lot of our statistical tests that we're going to use have this as an underlying assumption. You're going to need to test it before you run your test. You have to test the distribution before you run your analysis. This is just a little bit more about these distributions. This is 3 normal distributions. This is normal distribution with varying spread, but there's still a bell shape here on all 3 of these. Various means and standard deviations. How much deviation do you have in your data set? And whether it's offset left or right on that here. The main idea, and again, this is where I'm skipping. Remember that light speed thing? We could spend a lecture on this. Don't worry about it. Let it flow over you. Do the values in the data set you're working with. Take this shape. You have a symmetrical pattern that drops off rapidly and creates a bell shape. That's a question. There's a thing called the central limit theorem. This underlies a lot of statistics. I'll just say it here. For random sampling, as the sample size n grows, the sampling distribution approaches a normal distribution. So the more samples you have, the more hump shapes it will become around the mean. Again, this is just a different way of saying increase the number of samples to increase the power of your analysis. Again, we're flying. We're in the tunnel right now. Before you can conduct your test, you need to see if your samples adhere to this assumption. Most statistical tests have an underlying assumption of the samples having a normal frequency distribution. Okay, not a skewed distribution, not a bimodal distribution, a normal distribution. Before you can conduct statistical tests, we need you to make sure that your data meets the assumptions of the test. We have to look into the assumptions as we introduce the test, and we will do that. And just to say up the top, skipping, this, all formal statistical tests have assumptions and limitations. You have to know what those are, test them, and communicate them. Okay, when you're doing analysis. When you hear someone say non-normal, that means a frequency distribution is not bell-shaped. For example, t-test and ANOVA both have the assumption of normally distributed frequency, the normal frequency distribution of your samples. And both t-test and ANOVA have what's called non-parametric alternatives. So if the data fail to meet the assumption, you can use this other approach. How do we know whether our data meet the assumption? We can't run the test if they don't meet the assumptions. The proper technique is to screen the data prior to analysis. However, screening the data to meet assumptions of normality itself is complicated. Not everyone agrees as to how this should be done. The screening tests themselves do not work well for small sample sizes, which we often have in biology. There is much debate around this topic. If you bought that book, Whitlock and Schluter, you can look at 13.1 and 13.2. Read all about this. Again, here's some distribution: skewed, bimodal, bell-shaped, and we're assuming bell-shaped distribution. The problem is, especially when you get a small sample size, and I'll show you this later in the semester, it becomes very complicated to try to assess this. If you've got n equals 5 or something, it's difficult. And it's not clear that's the testing assumption makes sense. But then again, it doesn't necessarily always make sense to run a statistical test when you have sample size so low. However, the alternative is to not have a test. So that's not a good alternative either. So when you have small sample size, you're sort of sorting among poor options. And what we're going to do in the class, I'm going to teach you an approach that I think is a reasonable conservative approach, although there are controversy. I'll map out a plan for you. We've already started down the path. And this is what I've been trying to emphasize, and will emphasize the whole class, is best practices with your data. For example, doing this. Effects is only one part of this doves. And with effects, we're just asking, okay, is one median or one mean above the other? When the box plot thing is one box over the top, and then how different are they? And how does that difference relate to the variation within each sample? You can do all of that visually and doing basic statistics without doing a formal test. The formal test is confirmation or rejection of what you already see in front of you. So what we're going to do is create a histogram using R, and then we're going to visually compare the shapes to an ideal curve. So we're going to have, this is the process we're going to follow. Draw a histogram, and I'll show you how to do that in R, and then compare that histogram to this bell shape. Now, already you can see, does this look like a bell shape? Well, kind of. This one kind of does. You definitely have a peak near the middle. But again, when you have relatively small sample sizes, you start to get to the point where it's very difficult to ascertain such. We've already done this a little bit with our sort of strip chart or dot plot sort of concept. This is the histogram from this data set And this is just me turning this bell-shaped curve on its side. So you can try to kind of imagine this shape is reflected in this, kind of. Difficult to see. But you definitely, and we'll do this thing in class, where if you have a really strongly skewed data or extreme outlier or bimodal distributions, you can definitely see that in this, in the dot plot. Here again, this is turning the bell-shaped curve on its side. This is a histogram, the frequency distribution. So this is like an idealized frequency distribution. This is a frequency distribution of this data set. And this is a dot plot and box plot. So you can take a look and start thinking about this. Okay, so how are we going to test? We want to know whether or not this data set meets the assumptions of a normal distribution. As I said, we're going to create a histogram like this, our frequency histogram. We can look at the dot plot like that and just ponder it. Do we see something that looks like wildly skewed? And then we can do what's called a normal QQ plot. I'll teach you how to draw this in R. This is a relatively popular way of testing whether your data meets the assumption of a normal distribution. Is this normal quantile plot? Again, you can read the book Whitlock and Schluter 13.1, 13.2. If you go into the internet, you could probably find a dozen articles about this and different opinions. I'm not really establishing an opinion here. I'm establishing a process. And the process, by the way, that I'm describing for you, worst case scenario is you're going to learn a lot more about your data as you go through. Okay, so this is all good, and it's a robust approach. The normal QQ plot is part of that robust approach. And the basic idea is, can you lay a pencil on this and the dots are under the pencil? I know this sounds weird, but we're trying to ascertain a linear relationship here between the theoretical quantiles and the sample quantiles. We're in the, all you need to do is draw this plot and ask yourself the question. Probably a pencil on there, are all the points hidden? All right, looks pretty good. And I'll show you some that don't meet this as well as we go along. Here's an example where the curve of this, and I don't know what data set this is, but the curve of this is coming outside the pencil. See this? You definitely got a curve in this. This suggests that you've got a problem with the distribution, that the frequency distribution underlying the data set is non-normal. So if you see this in your data set, it should make you go, I don't know if I can run a parametric statistic on this. That is to say, I don't know if I can run a statistic that assumes a normal distribution if I see this curve coming out like a scimitar or something. I don't know. We're going to do this in R together, so don't get too worried right now if you're like, I can't understand what this guy's saying. We can also run a formal statistical test called the Shapiro-Wilk test. The Shapiro-Wilk test tests for a normal distribution. As in other tests, and this is the first time we've calculated a p-value, as in other tests, the null hypothesis is no different. In all statistics, we have a null of no difference. In this case, the null hypothesis is that the distribution is normal. We use p-values to assess. We'll talk about p-values shortly. For now, just understand that we can statistically assess whether a sample is normally distributed using the Shapiro-Wilk normality test, and we can generate this p-value. That's going to be part of what we're going to do. Okay, we're going to create a histogram. It's going to be this way, but we're going to create a frequency histogram and take a peek. We're going to do a normal QQ plot. This is very quick in R. And then we're going to run the Shapiro-Wilk test. That's a robust approach using multiple metrics to ascertain whether or not you can run the test to test for the effects or the test for the difference in your data set using a normal, a statistical procedure that requires a normal distribution. Bingo, bingo, bingo. Okay. What if you find that the data are not normal? So what if you run this and you go, uh-oh, I got this scimitar shape. I look like I've got some kind of weird distribution here. The data are skewed. Whoops, p equals less than 0.05. And reject the null of a normal distribution. Got a problem. Here's what you can do. A, ignore it and use a test anyway. Some tests are robust violations. How bad are the violations? What are we dealing with here? Is it marginal case? Is it clearly not normal? You can use data transformation. Okay, a lot of people, when they run statistics, end up transforming the data beforehand. There's lots of different transformations, log transformation, and so forth. Again, you can get the book and read 13.3 about transformations. It's arguable. Maybe we should do it in class, but I'm not going to. I've done that before with my own statistics. There's lots of questions about that as well. Whether or not we should run this test for normality, and if it fails a normality test, then run transformations to force the data to become normal, and then run the analysis. It's complicated. It's standard practice by some researchers, but there are problems in it. It's probably too confusing for this class, so we're not going to do the transformation. I'll just say, as I've said many times, remember principle number one is like, you're responsible. And so if you're like, I'm going to stand in front of people and give a talk and say, this strain of listeria is less virulent than this other strain of listeria based on this data analysis I did. If you're going to stand there and do that, you're like trying to tell people about the world. This is new information. Then you need to have figured this out first. You got to stop what you're doing, go to the literature, read the book. Don't listen. If your PI doesn't understand it, don't listen to them. I didn't say your PI is responsible. You are. You're standing there. The friggin' slide is behind you, right? You have to find out. So take the time to do the reading, get on the internet, Stack Overflow, whatever, and figure it out. Okay, I've got this data set. This is what people are saying. This is how we run the tests. I feel very confident that what I've done here is the right thing. Another thing that sometimes people do is use a permutation test to artificially increase your sample size. This is something you can do where you resampling and resample and resample and resample. It's becoming more and more popular to do permutation tests. Again, there are problems here, and it's too confusing for the class. We're not going to do permutation tests in this class. It's falsely increasing your sample size, basically, and increasing the power of your test by saying that the data that you've collected, I just resample among those. Whether or not this makes sense is highly questionable, I think. Although, again, some people do it all the time, standard practice. So these are some things to do. The last thing is, this should be D, is to use a non-parametric technique. Some analyses methods don't require the assumption of normality. So you can just go, you know what? I got a non-normal distribution. I'm going to run this non-parametric test version. So we'll do t-test and we'll have a non-parametric version of it. We have a NOVA, we have a non-parametric version of it. That's the way we're going to go in this class. I think it's, it's also controversial, but it is relatively standard practice. And what I'm going to develop for you, what I have developed for you, is what I view as a robust and evidence-based approach to running statistical tests. Although, again, item number one is it's your responsibility to track it down. If you're going to stand in front of people and claim that you know something about the world as a thesis, at a thesis defense or something, you got to slow down and dig in to be sure that you feel very confident that what you've done is correct. Okay. You can pause on this if you want to read this, if you want. If you've got large sample sizes, you don't have an issue. This is what this is saying. This is from some book. One of the problems with all of this is that some of these statistical techniques were developed, like I think that the t distribution that underlies the t-test was developed by a guy who worked at Guinness. Pretty sure this is true. I looked it up years ago. And so if you work at Guinness, that's a beer company, if you didn't know. It's a beer company, okay? If you're just like, oh, I'm going to change the quantity of yeast in these beer cans, and the beer can itself is the experimental unit, you can make thousands of cans. No problem, and it's super discrete. So you've got no sample size issue, and no problem, right? And so the idea of like n equals 4 or something, or n equals 7 even, or whatever we do in biology all the time, it doesn't fit. That's what this is saying. We got a problem. When you get less than 20, you start to enter into a scary realm. So then you can do a non-parametric version of the test. Okay, class distribution. And we're going to have a session in R where we talk about distributions more. We've already been talking about it. Outliers, obviously, I've been hammering you on outliers. We'll use outlier. Well, I'll talk about this for the whole semester. And I do that, and I will take points off of your assignments or whatever if you don't identify these. Because outliers can completely wreck your analysis. If you don't recognize you've got this in this data set, and you run the analysis, and you never did this chart, this fourth plot, and you don't know, then you can get results and stand in front of the world and say, here's some true facts about these fish based on the fact that someone sneezed in the tank, or some stupid thing happened, or you wrote the wrong number down. You can't have that. We can't have it. And the truth is, because human beings are flawed, and I'm not saying, P.S., I'm not saying all this because like you messed up and Ryan McEwen knows the best. Wrong. I've got screwed up data sets how many times? That's the whole reason I'm showing you. I once presented to my postdoc mentor a data set that had negative soil nitrogen values. And she was like, no, go start over. Just meeting's over. See you later. We can't have negative soil nitrogen. It's not a thing. It's only in the Marvel universe. MCU, okay. Every other universe, no. This happens all the time. So I'm going to ask you to find these. In this particular one, this was reasonable. This is income data. I'll show this to you later. It is reasonable. You can have people make that much money a year. If it was negative income, I mean, I guess maybe in economics it works, but if it's negative, like we said before, negative nail depth, this doesn't make sense. So, outliers. Variance. Okay, so I've talked about this already in class, but we're going to spend some time on it again. The basic challenge in statistical tests is, how do you estimate a value of interest from a sample of the population? Almost never do you have every individual in the population that you're sampling. And as I said in class multiple times, the variance in your sample, what you hope is that it represents the variance that exists in the real world. So if a vaccine trial, I can't trial everyone. I got to just trial a subset of people and say, like, does this Pfizer vaccine work? And do people get sick from it, or what? Does it have a contraindications? I want the sample of people I'm giving the vaccine to try, the trial, to represent the variation among people in the real world, young people, old people, whatever. Immunocompromised, children, because later you're going to then give that vaccine out or make some claim to the world about everybody can take this. Well, you want as much of that variance that exists in the real world to be captured in your sample. And then the basic challenge in a statistical test is to compare. Normally what we're comparing is some measure of central tendency, right? The mean, which is the arithmetic, we call these averages, right? The mean, which is the arithmetic mean. Median is the middle number in a sequence, and that's what's presented in a box plot. Or the mode, which is the most often repeated number. We don't see mode very often in statistics. Usually it's the mean and or median. And mostly when we talk about average, this is what we're talking about, the arithmetic mean. So this is something to be a little bit careful about, because when you present a box plot, you're presenting the median. And I do have a I've already said some words about that. The median is much more robust to outliers. So here's some distributions with these values arrayed along them. So for example, in the bell-shaped distribution, the median, mean, and mode can be right at the center, right at the tip of this. Here's a bimodal distribution where you could have one mode here, one mode there, the mean and median are in the middle. Here's a skewed distribution where you could have the median here, the mode there, the mode is the most often repeated number, and the mean is here. Here's a skewed distribution, skewed left. And so these are examples of the relationship of these measures of central tendency to different frequency distributions. That's what these things are, frequency distribution. Now, I think I've already given you this, but we'll just skim through it again. We talked about variance already. Variance is a formal measure of your data set. Variance is calculated like this, where you've got sum of squares. And you know, there's various ways. Variance is calculated differently depending on their tests or whatever. This is just like a generalized formula. Okay, again, we're in the that hyperspace light speed tunnel right now. Very fast. But this, I think, if you can kind of process what's going on here and really understand it, if you can just understand this, basically, you'll understand almost all statistics. Because underneath it somewhere is this, some version of this. This is the sum of squares here. This is this little bit of this equation, which we haven't talked about yet, where you've got the mean and then each individual value right there. And you're going to sum those. Here's the sample size. Down here, we talked about n being in the denominator of the variance calculation, and this is what the total thing looks like. You also hear degrees of freedom. This degrees of freedom by itself is a long topic. Obviously, I should spend time on it. We should take like half a lecture or something just talking about it, but I'm not going to. This is light speed. Wow. Understand that degrees of freedom is usually sample size -1, n -1. You're thinking about degrees of freedom. As you increase the degrees of freedom, you increase the power in your analysis. Hopefully that makes sense. You reduce the variance mathematically. One other thing to show you is this is how you calculate sum of squares. Now this is, again, I just want to show it to you for a minute. We're not going to do it in class. If I was a good teacher, we would do it in class. But this is not a statistics class, it's a data analysis class. So I just want to show it to you. So this is an example from the LeBron James data set. See this? This is number of games. This is how many points were scored in each game. 25, 12, 29, 22, 23, 31, 29, 31, 31, 37, 30, 27, 19, 15. This is the average of these values. If I just take the average of these values and do like an equation or a formula in Excel, I can just put the average right there. This is the individual value, 25, minus the average. That's where you get this. That's where this is sum of squares. And then you would sum these and then square it and then divide it by n, in this case is 14 minus 1. So just giving you a sense of what's happening here, because the variance in the data set is represented by how different each individual value is from the average value. If you had 1,000 here, this is going to make your variance go through the roof, right? That would be an outlier, for example. If you didn't get that, it's okay. But if you did, that's going to help you understand the fundamentals that underlie statistics. And again, you can just be like, okay, I need to figure this out. I'm going to run this. I need to really think about sample variance and get that Whitlock and Schluter book or some other books. This is like really basic, analysis concepts. And here's the variance. You might hear sometimes standard deviation. Now I've taken the square root of this. You might hear about standard error. Standard error is S divided by the square root of N. Okay. Remember, underlying it is all this stuff I just talked about. Sum of squares is in here. Yeah, this is what it looks like. And coefficient of variation, sometimes you'll hear this reported. That's a standard deviation divided by the mean times 100. These are all just different ways of estimating variance in your data set. Again, we're going like a warp speed situation here. But I do want to introduce these variance concepts. And you can click back through this just to think about it. I'll give you the PowerPoint slides. You can click back through it or look for other places where this is all being explained. Yeah. Okay. So I want to talk about how to test for normality. I've already mentioned this. We can do a Shapiro-Wilk normality test. Yeah, we already talked about this, so we're good. Now, on to effects. So if we're going to estimate effects, the goal of data analysis is often to investigate your potential for effects. If I get one drug, you get a different one. You know, I got drug efficacies, fire in a prairie, or whatever it might be. Antibiotic treatments. Treatments in an experiment, for example, or whether one variable affects another. You can draw some conclusions from apparent effects, for example, noting that nearly all of your experimental seedlings die with one fertilizer, while nearly all of the others grow vigorously, is strong evidence of effects. So if I'm like, okay, I give all these seedlings this fertilizer and they die, okay, and everybody else lives, that's some strong evidence. We often want to also quantify our certainty, and this is what we do through statistical testing. For statistical testing, we have two main big concepts to touch on. The practice of hypothesis testing and p-values. And we've already talked about this a little bit, but I just want to talk about it in a bit more depth. Scientific research is often focused on hypothesis testing. For the purposes of data analysis, this takes a particular form. A null hypothesis is established, that is no difference or no effect, nothing is going on. Then you do a study, and you'll often analyze your data in an attempt to project your null hypothesis of no difference. The null is no effect. All good hypotheses are rejectable, and in statistics, you'd formally attempt to reject a null hypothesis of no effect and measure your confidence using a p-value. Okay. So here is a little lecture about what is a p-value. We've already seen p-values in the class a couple times, but haven't really delved into the topic. So one thing I want to say is that there's a lot of complexity around the use of p-values. Here's an interesting article that's from a website called 538. Again, we're in a hyperspace tunnel here. I'm just going to give you a working comprehension to do my best to teach you how to use p-values effectively for statistical testing. Okay, what is a p-value? The p-value is the probability that a difference of the magnitude revealed in the analysis would occur if the values were not different. This is very hard to understand. Almost no one understands this. Even, and this is what this article is about. It's like if you interviewed a bunch of statisticians, they couldn't explain it. It's hard to explain. If the null hypothesis were true and the values were not different, the p-values tells us the likelihood of a result as extreme as what we have found. A different way to think about it, which is more or less correct, is a false positive result. This is called a type 1 error. And here's if you want to pause and just read this, or go to Whitlock. This is from some other book, but you can go to Whitlock and Schluter or some other text and read about it. Yeah, the smaller the p-value, the more strongly the data contradict HO, which is the null hypothesis of no difference. Okay. P-value is denoted by capital P in italics, by the way, normally. Okay, so this is the way to explain it, I think, in class is it's the probability of crying wolf. When you yell wolf and there's no wolf, that's the p-value basically. Another way of thinking about it is getting a positive result when you do not have COVID. That's a false positive result. What's kind of interesting is when I first taught this class, saying false positive result, students didn't know what that was. That's why I came up with this crying wolf thing. But now, so many people have had taken stupid tests that you probably know what that, I probably don't need the crying wolf anymore. Just say false positive result. Okay. The p-value is a probability of crying wolf, a type 1 error or false positive. It's a probability of having a difference this extreme if the means are not different. The standard for determining if a difference is significant is a result where the test results in a p-value that is less than 0.05 or equal to. If your statistical test yields a p-value that is 0.05 or less, then you reject the null hypothesis. The null hypothesis is no different. Okay. So you'd say there's no difference here between these two. That's the null. Now I'm going to run a test, see whether in fact there is a difference. The difference then would indicate if the p-value is less than 0.05, you would be able to say LeBron James had more assists in games that the Cavaliers won. Statistically, I have a statistically significant result, or I have statistically significant evidence that that's the case, beyond just the visual observation. And the p-value is the probability that they're not different, but that you've got a result this extreme. Probability of crying wolf. Well, how do you think about that? Well, if you take 0.05 times 100, that's 5%. So biologists are saying, kind of, this is not perfect, but this is just me trying to explain it. People never really thought about it. They're saying it's okay to cry wolf if there's a 5% chance, 5 times out of 100, that the wolf is not there. Or alternatively, you are 95% confident that the wolf is there before you shout. The p-value is never 0.000, never goes to 0. There's always a chance that you're crying wolf. Always a chance. When our test yields a p-value that is less than or equal to the critical value, that's what we call it, 0.05, then we reject the null hypothesis. We're pretty sure that there is a wolf, and we say wolf. We're pretty sure there's a difference here. How sure are we? 0.00068887. So that's less than 1% chance. Significantly less than 1% chance. We feel very confident. This is actually the p-value for this test. We felt very confident that we can say out loud in a publication, we found that LeBron James had significantly fewer assists in games the Cavaliers lost. So we've looked at this. The box looks higher. This looks like fewer. This is 5. This median is 7 or something. The variance looks okay. We've got one. This looks like something here statistically, just visually. Now we've run a test and we can say this is our level of confidence that in fact this green box is higher than this red box. This is a probability that we're wrong about that this is higher. Okay. So I mentioned in our bingo, we have UFO asterisks. This is what the asterisks are usually. 1 star means that your probability is less than 0.05. 2 stars is less than 0.01. 3 stars is less than 0.001. And I was told a long time ago by my mentor when I was an undergrad, that's it. You can't go less than that. Just don't. You don't need to report values less than that because it becomes preposterous. Preposterously small values. Okay, alternative kind of error is a type 2 error or a false negative. It's not calling wolf when the wolf is out there. Then you got your sheep gets taken away. That's not good. Again, updating the lecture for modern times. I wrote this lecture the first time before COVID. Students had never heard of a false negative, but now everybody knows what a false negative is, unfortunately. Sad, but true. So the idea would be you get a negative test, but you've got COVID, which I think is a thing. Anyway, sometimes I'm not so good. I'm just saying. On the disease dynamic and whether you make an error in the test, blah, blah, blah. Anyway, so what do we do if the p-value is above the critical value threshold? So what do we do when p is greater than 0.05? So here's an example of a two-sample test. Just quickly looking at this. This looks like points, wins and losses. Remember that? P-value 0.9. So there's no evidence here. We fail to reject the null hypothesis. The null hypothesis is no difference or no effect. This means we cannot statistically distinguish between the groups being compared. We cannot make a statistically supported claim about wins and the number of points in wins and losses. Now, when you're doing a thesis kind of project and you're running your analysis and you get a p-value that's greater than 0.05, that means there's no effect. Sometimes that can feel bad because you're like, I just did this whole experiment and I scared these fish and I scared their parents too, but now the statistics show me nothing happened. Is that sad time? That's the question. Does this mean you can't be a science? Greater than 0.05? No, you can still be a science. Even with even with values greater than 0.05. In fact, a test result that's p-value greater than 0.05 or above the threshold value that fails to reject the null hypothesis does not mean your experiment was useless. It tells us important information about the world. We go, okay, for example, in this data set, which we looked at before, with this box plot of LeBron James, points, losses, and wins, we go, there's no evidence that the number of points differed between wins and losses. Guys scoring 27, 25 points a game, just all the time, period. There's no difference here. This is important information. I mean, just as an example, in this particular thing, you could say, if you're a statistical consultant for LeBron James, you gotta keep scoring, of course, but that's not where it doesn't make a difference in wins and losses. That's just baseline. So there's other attributes of your game that you can think about that might make a difference. Particularly, can you get the number of assists up? Sorry. We got really good evidence here. That makes a difference. Anyway, one more thing. There's a tremendous difference between a study that yields a result, which fails to reject the null hypothesis, and a study that yields a result that is too vague to come to any conclusions. Okay. If you can confidently say drug A and drug B have the same effect on infection, okay, maybe if you're the manufacturer of drug B, or if it's in your thesis project and you wanted it to be higher because you're like, I did this new drug, but there's no effect there, you might be like, but it's still important information. It's good science. Because you can't tell doctors then to give drug B instead of drug A. It's like, well, it's the same. I cannot statistically distinguish among these. I can't separate them. That's good science. If your results are, we don't know if drug A and drug B are different because our statistics are too messy, because we have pseudo-replication, or we don't have enough sample size, we have some other screwball thing to happen. That's being SOL by design. You don't want that. So it's really important. This is a really important point. You need to be able to tell me what's the difference between a statistical test that yields no significant difference and a study that can generate no statistical test that's valid because it's too messed up. All right. The last thing is sample size. we've already talked about this at length, and I don't want to go into it again. But again, this class has not that many concepts, and we just cycle through those the whole semester, more and more and more, until it becomes hopefully innate. The sample size is the denominator of all these variance estimates, which we went through. This is standard error here, I think. Mathematically, more samples makes your variance decrease. Okay. The calculations of a in the calculations of a p-value, sample size plays an important mathematical role. Literally, your power to answer the statistical questions you're asking increases as your sample size increases. As a practitioner, you want to increase N. As a viewer of data, you want to know what N was. You want to know what the sample size was. If you're talking about polling data, you're talking about whatever kind of data. You're talking about whether the dishwasher is efficient. You know, this is in your regular life too. Certainly in science. You want to have more N as a practitioner, and you want to know what the N was as a viewer. And this is why, of course, I teach you to use a Bohr plot as the very first thing we do, because the sample size is literally displayed on the screen. You can see it. Yeah. Okay, so those are the minimum concepts you need to be able to statistically compare groups. Admitting that I pulled you through a vortex here, and that many things were passed. We passed over many things, and we're going to turn right around now and start running statistical tests. And we're going to leave all of the detail for you to chase if you want to. Like, oh, I think I'm going to go figure out the math underneath all this. It'd be great if you do that. But for the purposes of the class, where I want to get you to be maximally empowered is to start practicing, to use the tests, use the tests, bring in data, analyze data, bring in data, analyze data. I think that's where we need to get to. And so we'll have to just leave it there. Those are the things you need to know to statistically compare groups.